Hello everyone, my name is Jarosław Szymczak. I currently work at OLX Berlin, and today I will show you our solution for automatic image moderation. I'll start with some agenda. So at first I'll introduce you to what exactly this image moderation problem is, because it's not that straightforward as you could think. Then we'll go through the brief sketch of the approach that we use. Then I will dive a little bit deeper into what methods we use to extract the features and create a classifier. It will be followed up by a few comments on learning from imbalanced datasets, how to proper train, test, and evaluate them. And finally, I'll conclude with telling you how we made this live and how it works in production. So let's start with OLX. OLX is a so-called horizontal classifieds site. And it basically means that if you have this old table that your grandma gave you, but you don't really want this anymore and you think about replacing it with something new, you can use OLX for both, to sell the old table and to acquire a new one. And the same goes for any other categories: cars, electronics, real estates, and so on. So OLX is the biggest classified site in the country when I come from. I come from Poland. It is also the biggest classified site in many other countries, but in general we have presence in 130 countries, processing 16 million ads, or we call it listings, per month. And the problem that we're dealing with is that we want for the service to be the good quality service, so the users come back and use it with pleasure, both sellers and buyers. In order to do so, we moderate ads. And my colleague, Vaibhav Singh, tomorrow will tell you in general about moderation. Today I'll be focusing on moderating the images and images only. So basically, to ensure that our sellers aren't hurt, we don't delete anything automatically. We just choose from all the images that come to sites, we choose the ones that we think that are suspicious, and they go through manual moderation just to confirm that they are indeed unwanted images. I mentioned unwanted images, so what exactly this is? Apart from obvious not safe for work images where some people show a little bit too much and it really shouldn't be on a classified site, but maybe somewhere else. We also sometimes are bounded by some legal obligations. Like, for example, in India, due to some legal reasons, we don't allow people to put pictures of people in general in classifieds, because it leads to some legal problems, and simply we don't allow it. So we detect humans, and if there is a human on the picture. By the way, these all are stock pictures from Google. I just wanted to ensure that I don't violate any laws, but they are like the ones that I'm talking about. So basically, yeah, humans in India. In Poland, a big plug are stock photos. So as OLX is a super popular site there, a lot of companies also would like to advertise there. And they advertise their stock photos. They add contact numbers on these photos, or some super occasion, buy it now, and things like that. This deteriorates the quality of our service, and we don't want things like that. So that's basically it. Every country has, what I mean to say is that every country has certain rules, and certain photos that are allowed in one country not necessarily need to be allowed in the other one. So we created a pipeline that uses the algorithms to create the models, and models are individuals per country. So now I'll tell you briefly how this approach looks like. So we take both image features and so-called classic features into account. For image features, we use neural networks as a black box. Basically, the state of the art for image recognition nowadays are convolutional neural networks. And they allow you to convert, after appropriate resizing, convert your picture into an abstract vector of numbers. And this vector represents, in an abstract manner, what is the content of your image. So these features extracted from image, we concatenate together with some classic features. So not too much, because we still want that our classifier mainly focuses on image, but we add things that we think that are necessary, like categories, price of the item, or whether it comes from business or private person. As I mentioned, if it comes from business, there is much higher probability that this stock photo is actually a stock photo, but sometimes having only image, you cannot really detect if someone made a really good picture, right? And it's not something that you would like to remove. So after concatenation, all of that is fed to XGBoost, and I will tell you more about each of that on the following slides. So, image features. If it was 2011, there were no convolutional neural networks around yet, at least not popular. Not popular, well, well, AlexNet won ImageNet in 2012, and that's when the boom started. So basically, before that, normally when we would approach the problem, you would try to find the features on your own. And for example, for these stock images, you have this nice background, white or blue, so a color histogram would be a really good feature to extract. To detect humans, maybe it would be good to find some edges, and then from these edges construct some more features that would actually tell you that, yeah, there is a human in the picture. And on each type of pictures and each type of problem that we currently have in different sites, we would need to come up with different features ourselves. And the main focus would be on feature engineering. It all has changed with convolutional neural networks, because now you can either use the transfer learning on fine-tuning, that I will be talking on the next slide, to a little bit adapt them to your problem and to create this abstract way of representation of your image. So basically, convolutional neural network consists of certain layers of neurons, and they can be interpreted as more and more complicated image features, from edges to certain shapes, to bigger shapes, and so on and so on. So they are trained on the large ImageNet dataset, and you normally don't train them yourselves from scratch. So you take the ones that are able to recognize this large amount of images in ImageNet dataset, and they focus on a lot of things that you could extract from there. So basically, the feature engineering part now is simply here. You don't need to do it anymore. So basically, this approach of putting the image into a network, and then just before the output of this network, you have this last layer of thousands or so feature, and this is your abstract description. And you can further down the road use it as these abstract representations, as your features. You don't interpret them normally, they are just some abstract way of representing it. If you have a more specific problem than the one, for example, that simple object recognition like in ImageNet, and your pictures are more specific, you also do something called fine-tuning. So normally this very general features like edges and shapes, circles, and so on that you would extract wouldn't change, you still want it. So you just freeze the layers that are more or less responsible for this. And then you train again the network with those layers frozen. And then you use it basically in a transfer learning setting, or in our case at least, we use it again in transfer learning setting. So the first model that we used was an inception model. This model comes from Google, and it won also one of the ImageNet competitions in 2014, I believe. And we used the version from MXNet that was trained on 21,000 different objects. And this network performed really well. We used it for various tasks, not only for image moderation, so it was very easy to adapt from other problems to image moderation problems, and that was the main reason why we chose it at the very beginning. So it basically is able to recognize 21,000 different things, and when we were testing it with some pictures from the site, we were really impressed with how detailed some annotations were. Like, we took some antenna that the user posted, and it actually told us that it's a Yagi antenna, not only that it's antenna. I had no idea that this is this kind of antenna, and it actually was, so I was really impressed. So basically, another network that we use, because we thought maybe we were wrong, maybe we were right, that was a hypothesis that Inception network was trained to recognize these objects. So if you show it the phone, it recognizes the phone. It shouldn't really matter that you have nice white, black, blue background there. Phone is the phone, and I don't believe that in ImageNet you would have something like black background to as one of the things that it would want you to classify. So we decided to fine-tune it. However, we fine-tuned different network, VGG 16, because it was simpler, and because, in contrary to MXNet, Keras allows very easily to freeze certain layers. You just set the parameter layer.trainable to false, and it's frozen. And basically then you continue your learning on the couple of last layers, and you do your fine-tuning. After doing so, you use it in this transfer learning setting as well. So that's it for images. Now it will be even shorter for listing features, because there is nothing complicated here. When we use category, we simply one-hot encode it, or we get dummies, or whatever you call changing it to a bunch of binary variables. Plus our other classic features like price and binary feature, whether it's business or not, do not need to be really encoded. So afterwards we concatenate it, and we used gradient boosting on top of it. So why gradient boosting? Because it's parameterizable, and maybe I'll start with what boosting is. So boosting was an idea of Robert Shapiro, of using the weak learners to create a strong learner. So basically, imagine that you have a problem of classifying with pluses and minuses, but your classifier is just one-dimensional, and you can make either vertical or horizontal line. So you can use a boosting setting to create a strong classifier that would fit a more arbitrary shape than just vertical and horizontal ones, by applying in certain rounds the correction of weights to your examples. So basically you see where you made an error, and for these examples that you made an error, you increase the weight. For the ones that were correctly classified, you decrease it. And then again, you do the training, and again and again and again. Normally it's not 3 rounds, but many more. And then your final hypothesis is weighted, and you have the strong hypothesis. So that was adaptive boosting. Gradient boosting is similar, but not exactly the same. So it is much easier to explain it in regression rather than classification setting. So basically, when you have the regression, regression is the problem of predicting the number rather than a class. So you have some expected number that you want to predict, and you have the output from your classifier. And the difference between what you wanted to predict and what you predicted is called residual. And gradient boosting works in such a way that it starts with some baseline classifier and then it fits those residuals. And in each round, the residuals of the whole classifier are found and you simply try to correct your errors. And the reason why it's called gradient boosting in such a setting is because the residual is actually an individual example contribution to the gradient of this main part of mean square error. So you take aside the root, you just have the sum of squares, and when you differentiate, you have the x squared equal to x, and then you have your residuals. So when you apply a similar thing to classification, you don't have any more the residuals, but you have something called pseudo-residuals. Anyway, it works really well, what proves a lot of Kaggle competitions won by using this. So we use the implementation called extreme gradient boosting. It's very efficient, quite well known now, I believe. It has interfaces in R, Python, you can run it on Yarn, and basically it has a little bit differs from what you can find, for example, in scikit-learn or other packages, because it has a lot of regularization, the classic regularization like L1 and L2 included already in the formula for creating the trees. So it works really well in practice, and to start using it, it's quite easy. Plus, you can really do a lot of parameterization with ensuring that your model is regularized so you don't overfit to the data. Plus, if you underfit, you can also make sure that having enough rounds, you correct your error until it's sufficiently low. So now a few words about class imbalance problem. So as you probably suspect, the number of bad images is not so large. So most of the images that we receive from users are okay. Only 1% of the images is something that we would consider bad. Even less something that we would consider severely bad, but let's focus on bad. So in ratio 1 to 99, it's hard to create a good model. We're just telling this from experience. You need to change this ratio, and we found out that changing this ratio to roughly 9 to 1 is okay. So basically, when you have this severely imbalanced problem, you just make it an imbalanced problem, but more, less severe imbalanced problem. Let's call it like that. And there are a couple of ways to achieve it. When you have this class, when you have a lot of examples, and the class that have few examples, you can either decrease the number in one or increase the number of the other. Not really a lot of other possibilities to change it. And you can do it randomly. When you have random over or under sampling, there is a fancy method called SMODE when you generate some artificial examples, and it has an application when you don't really have the source for acquiring more data. We do. So we actually have more pictures than we really need to create the models. That's why we do undersampling and not oversampling. So we simply randomly choose the positive class and have all the pictures from the other class, so we don't lose the information about the bad pictures. And when you have the data, I think it's the best what you can do in such case, if you can acquire more examples of this small class. So that's how do proper training. Now, how do proper testing on what kind of ratio you should test your data? And the answer is simple: use the real life one. You really need to use the real life ratio if you want to know how actually your classifier performs. and not by some area under curves that I'll mention in a moment, or some other measures that are not directly applicable to business, because that's what will be the same regardless of ratio. There are some measures that won't be the same, and if you don't use them, you will find out that it won't be the same until you actually apply it on production. So I advise not to do it, and for proper testing, use the same ratio of the data, or even better, use the data that you would apply it on. So just for example, in our case, we just take 2 weeks of data that were not used for training, and just exactly on this data with unmodified balance of classes, we evaluate how good the model performs. Now, a few words about evaluation. So if you evaluate on this 99-to-1, achieving 99% of accuracy is quite easy. You just say that everything is good. It's also totally useless. So there are other better measures to do so. The classic of classics for binary classification is receiver operator curve and area under it. And it basically tells you the trade-off between the true positive rate and false positive rate that you have. And it can be interpreted as a concordance probability, which means that if you have your positive class and negative class, area under curve can be interpreted as the probability that one will be bigger than the other, the score that you assigned to it. So it's very robust against your proportions. So on our train set, 9-to-1, and on our test set, 99-to-1, it's roughly the same. So for this part, in actually knowing how good your classifier can differentiate between the two classes, it's a really good evaluation. But when we have business, and the business will ask you, okay, so how many of the pictures actually we can evaluate? But don't waste time of our moderators. Yeah, so at least more of the pictures that you send to this queue should be actually bad, and that actually means that your precision should be at least 50%, because the precision is when your classifier gives you some output, you check what's the percentage in this output that classifier gave. You do some threshold for that. So if the classifier, for example, gives you, and only in such case you can do it actually, if your classifier gives you the probability. But only if, or it doesn't have to be probability, but the score. So only if score is bigger than something, then give the output. And in such output you predict what's the percentage of the things that you actually predicted correctly. That's precision. Another thing is recall. So you have all those images on the side that are bad. And recall is something that tells you what's the fraction of the images that you actually found from the site. And there is always a trade-off between both of them. So this trade-off can be bigger or smaller. And I really recommend to create something called precision recall curve. And one of the things that you can do, you can plot it and you can calculate area under it. It will not exactly tell you whether it's good or bad, because it depends on the shape, what we will see in a moment. But it's something that is worth considering. So, just one last thing I mentioned at the beginning. So very often in business requirements, someone will want you for your classifier to have 98% accuracy. By what they mean 98% precision, or in this case of images, like 50% precision and so on. So then when you have this trade-off, there is another very, very well-known trade-off between precision and recall that I don't mention here because we don't use it. It's called F-measure. I think that the precision recall curve is better because it shows you on every possible threshold. F-measure is calculated on 0.5, so it's not exactly well interpretable. Sorry. So I made a comparison for our models using Inception 21K and VGG 16. From the perspective of receiver-operator curve, it's the same. It's also the same for the training data. If we take a look at precision recall curve, you see that for this class of good images, it looks totally different, so it's very easy to predict it. For the class of bad images, which in this particular case is class 1, for precision equal to 0.5, we have a recall of 0.27. It doesn't seem to be spectacular, but also it is actually okay for our business, because what we do is we partially educate the users. So the users are our friends. It's not that we are some kind of police that we want to find all the images and delete everything possible and penalize everyone. No, we just want to educate them so they know that we want to have this good quality on the site, and it's sufficient that we find at least some of those images, and that it gets popular, especially for frequent users. Some of if it's their often behavior that they put, for example, the stock images, one of them will finally be caught, and they will know that we don't allow such thing. If we compare it to VGG 16, if we go back for a moment, sorry, you see that this area under curve is 0.38. For receiver operator curve, it was exactly same. Here, area under curve is 0.41, I'm sorry, and the difference is like 7%, right? So in this measure, it's a 7% increase. So on ROC, there was no difference. In precision recall curve, area under the curve, it's 7%, but actually in recall at certain precision, what is the most important in case of such requirements that I mentioned, you have a 50% increase. So the lesson learned from here is that actually you always should think of the actual measure that you want to optimize. What is your goal? You shouldn't just use ROC because that's the most popular thing to do, or you shouldn't use any other measure because it's popular. Just think what suits your business and what you actually want to optimize. What are your business requirements? What are other restrictions that you have? And simply apply your measure to those restrictions. Now a few words about going live with the product. So we have this model, we did it, we created it, we evaluated it, it got accepted, yeah, we accept such quality, let's go live with it, please make it live. How is the best approach to do it? So first thing is make it reproducible. That's one of the important things, and this tool that recently is used very widely is Docker. So Docker is like a bunch of these small virtual machines, and each process that you run with Docker runs in its own machines, and you can use Docker Compose to make these processes work together in a reproducible way. So they will, in theory, in practice it sometimes differs, it should run exactly the same in your development environment and in your production environment. One of the things that is hard for reproducibility are graphic cards. So when you use convolutional neural networks, you need an okay graphic card that works well with CUDA and cuDNN. And actually, you don't need to install neither CUDA nor cuDNN because NVIDIA has a Docker image with this. So you just need to provide the drivers and use their image, and you just then need to care to install your libraries in Python, and you're ready to go. However, for composing, you need to specify which graphic cards you exactly want and which devices you exactly want to be visible in this container, this small virtual machine that Docker provides you from your computer. And this is not really reproducible because different computers have different configurations. But NVIDIA came up with this NVIDIA Docker Compose wrapper, and it simply changes your Docker Compose file to NVIDIA Docker Compose file that is used to create your Docker environment. So this is really useful and makes life much easier. Now, when you want to create models because your concept changes, or for example, now moderators, thanks to the fact that you implemented your solution, they have much better ratio, so they can evaluate much more bad images, because previously they had like the random sample, and now you send them actual bad images. So this proportion that they work on starts to change. And you want to update the model because you now have more data. How to do it in a reproducible way, or you want to launch it in another country. You already have the algorithm, you just need a new model, so you can apply the whole pipeline that you applied for one country to another country. And for this, we use Luigi framework. So Luigi framework consists of tasks, and these tasks can be formed into pipeline. So the task has Luigi parameters that can be directly put in a command line when you call your task. Then they have the requirements. So their requirements are, at least the ones that we normally use, are other tasks. And when Luigi requires these other tasks, it checks if this task was done by checking if the output of this task exists. So basically, when you have some part of your pipeline already done, then Luigi will just use it. If you don't have it done, then it will start the process and create your output. So for example, if I want to compare a couple of models on the same test set, this test task will run once to collect the data, process the data, extract features, then train with the first classifier that I mentioned there, test, write the output. But for another one, it will just train again. All the intermediary parts will be done because the output will exist there. The thing is that you need to take care of this yourself. So for example, you define what the output will be. So you should be sure that your output is determined in a proper way, that you take your parameters and encode them, like for example, the country that you do it for, the dates that you do it for, some hash from the dictionary of parameters that you used, things like that. So it's actually reproducible. And Luigi normally provides you with Luigi daemon that waits until the task is executed, and you see this dashboard with number of tasks that were done, that are running, and that are pending. And you can also take the last task, which everything depends on, and click on it, and you'll have this nice visualization that you'll see that these tasks are done. For example, in our case, we have one task to download pictures from one day that we can then run concurrently. And then it's all aggregated, transferred to a certain input to neural networks, to feature extraction. Then we have these concatenations of features and classic features and image features, then train and test. Some tips about using Luigi. When you create the output, when you use the output as it, Luigi ensures that first you write to some temporary file and then it is renamed. But you can also take the path of your output because you have the library that only accepts the path. In such case, your file is created, and imagine that you have some error. Some error occurred, and actually this file is only written until the half. As I mentioned, Luigi checks dependencies based on existence of the file. So your whole process will start failing if you start writing to the actual output. What you should do is to write to a temporary file and then at the very end rename it. Or just use the Luigi output stream rather than a path. It also will cover it. Then other thing is that you can define with static requirements. So this well-defined pipeline, or you can yield some tasks. For example, if you want to download some number of images and you don't want to make the too big traffic to servers, let's say, you can check every time how many pictures you downloaded in your last tasks and dynamically decide if you want to download another day or not, for example. That's what we did in one of the projects. You can run things concurrently, just when starting the process, add workers parameter. The only thing that I didn't find, I'm not saying it's not there, I just didn't find it, is to restrict some tasks. For example, training of XGBoost, in our case, is already parallel. We don't want to further parallelize it. And normally what we do is that we run these tasks for downloading data concurrently and then again run the task afterwards without the concurrency. Maybe there is a way to do this, I didn't find one, so that's one thing. Another thing is that for simple workflows, when you create your parameters and you want these parameters to be like inherited ones, so you have certain time interval, or this should be run on certain GPU if you have many, and so on, then in every task, at least that's how we did it, we created this parameter. So we said that it's time to stop this madness and introduce the simple inheritance for that, and then created some basic class like that, it's very simple now to create this simple dependencies, that something depends, just adds a new parameter and all the rest is executed with the very same ones. I'll not go into exact details, but you'll feel free to test it. As for live process, we have a Flask API with G-Event, and it's hosted in AWS. The whole architecture looks more or less like that. So we use MongoDB to store our ads that are coming from some other process. Then it's fed to learning process. It outputs the model. This model is used then in our endpoints. Our endpoints are monitored by Grafana and New Relic. We also have Slack attached for logging purposes. It's very convenient when you have things in different Amazon machines and they just simply, the logs are also outputted to Slack, and then you have it on the Slack channel, all the errors that happen live. We send data in batches, and it's quite important that you don't process your photos one by one because of vectorization costs. So if you do it one by one, it will be very inefficient. So we ensured that we have the data sent in batches and we receive the batches. But if for some reason you, for example, would like to create some API that processes images and would like to be able to consume it one by one, then ensure that before predicting you batch it. Otherwise, your system will be very inefficient. And last but not least, we use Grafana for performance monitoring together with StatsD and Graphite backend. And it is very simple, and you can do a lot with that. We have a couple of flat screens in our company with key statistics to be sure that our live services work properly, and we are very happy to use it. You can use different backends, of course. Grafana is very nice front end. So at the very end, I'd like to acknowledge my colleagues that were working with me on this project, Vaibhav Singh, Jaydeep De, and Andrzej Prawat. Thank you very much for your attention.